All right, this is Chemistry CP on Friday, April 23rd, 2021. The question had arisen, how do we do half-life problems? Of course, you'll need a calculator. The formula for half-life says the final mass that you end up with is the product of the initial mass that you start off with times 1/2 raised to the number n. And n is not an integer, by the way. N is the number of half lives. There you go. That is what n represents. N represents the number of half lives. So, for example, carbon 14 has a half life of 5,730 years. Nice. So, if the age of a sample of something is, oh man, so if we had a sample that was 11,460 years, how many half-lives would that be? Well, that one is simple. The number of half-lives is equal to the age of the sample, or the amount of time that has gone by, divided by the half-life time. So in this case, 11,460 years divided by 5,730 years. The units cancel. And thanks to modern technology, I have a calculator. 11,460 years divided by 5,730 years. Enter is equal to 2. Your random choice student worked out to be 2. I may have to fail you, child. I'm thinking pretty seriously about failing you. Yeah, okay. Here, let's do some other more reasonable students. So, as a second example, a age of 9,000 years would mean the number of half-lives is 9,000 divided by 5,730. Enter is 1.57068068. I'll just call that 0. I'll just call that 1.571. There we have it, 4 sig figs. 1 sig fig, 4 sig figs. Oh, look, 4 sig figs, 4 sig figs. Great. Well, you need this number, and that's how you get it. It's the ratio of the age of the sample divided by the half-life for that particular substance, in this case, carbon 14. Now for the mathematically more challenging part. How do we solve for n if we know the other two quantities? Right? That one is a much harder problem to go after mathematically. And so, to kind of set you up for it, I'm going to try to review or teach you, depending on your math teacher, about logarithms. Yes, logarithms. To begin with, what is 10 to the 0 power? Turns out, any number other than 0 raised to the 0 power is just 1. So crazy but true from math class. So 10 to the 0 power is 1. Anything other than 0 to the 0 power is 1. 2 to the 0 power 19 to the 0 power, and so forth. What then, pray tell, is 10 to the first power? Yes, 10 to the first power is indeed 10. 10 to the second power. Yes, 10 to the second power is 100. 10 to the third power. 10 to the third power is 1,000. And so now to try to explain a little bit about logarithms. A log in base 10, which is what this generally means if you don't write anything, of a number such as one of these numbers, like 1, is the value of the exponent that goes on top of the 10. So log to the base 10 of a number is the value of the exponent. So the log to the base 10 of 1 would be indeed 0. The log base 10 of the number 10 would be 1. Log base 10, I'm not going to bother writing the 10 because it's implied if we don't write it, of 100 would be 2. You can see the pattern? Woohoo! Log of 1,000 is indeed 3. Now, the cool thing about your calculator is you can ask it what is the log of some number between 1 and 10, or between 100 and 1,000. I wasn't recording any of that. I have to do it over. Oh, no. It is recording now. Okay, I'm not sure if I recorded this or not. I think I did. The point is, the log is the value of the exponent of 10, base 10, that is the result of 10 raised to that power. So consider the random number 437. There is some value of an exponent, I'll call it x, such that 10 raised to the value of that exponent is 437. And as you can see by looking at what I've already written down, 437 is somewhere between 100 and 1,000. So this mystery value of x is somewhere between 2 and 3. That's all I can tell you right now without a calculator. Somewhere between 2 and 3 is that value of x such that 10 raised to that value will equal 437. Now, the beauty of your calculator is that it can go figure it out for you. The feature is the log button on your calculator. And if you type in log of 437, it will give you that value of x. That will be its output. So I have a TI-84 Plus Color Edition graphing calculator. If you have one of these, then the button you're looking at would be the log button. And this is base 10. There's also the natural log button, which is base E. E is an irrational number. In addition, you might merely have a Casio, which I would expect also has those buttons. But let's say you have no calculators. All you have is a measly stinking phone. Well, there exist phone apps. Here's one. Why, look. Divide, multiply, subtract, add, equals. What more could you want? Well, you might want a log button. So what you can do is with your phone, tip it to be in landscape orientation, and voila, it turns into a scientific calculator. And so now, if you look around, there's the natural log button. There's the log to the base 10 button. There's that irrational e to the x and 10 to the x. So everything you need is here, including this x to the y button that I might refer to later. So even if you only have a phone app, it is possible for you to do this stuff. I'm going to use my calculator. Activating my calculator. What I'm going to type in, of course, will be log, which is a single button. You don't type log. 437, close parentheses, enter. Beep, beep, beep. And as predicted, the number displayed is between 2 and 3. It says x is 2.6404811437, ... Okay, I've written down enough of it that I care for. My claim to you is that this value of x is the log of 437. And that means if I go 10 raised to the power of 2.64048, that number is going to be approximately 437. I say approximately because I didn't write out all those digits. I can, of course, just go second answer on a TI and type in 10 raised to the power of second answer. So that copies the last number in my display, paste it there, and voila, out pops 437. That is, in a very short nutshell, the properties of logarithms. There's a little bit more. I think I'll share this one with you. The log of 437,000, oh my goodness, is equal to the log of 437 plus the log of 1,000. And I bet you don't quite get why I can make that claim. So let me back up just a little bit and try to prove this to you. So if I said I have 100 times 1,000, you would say, oh, that's easy. That is 100,000. Yes. So a property of logarithms is, well, this is 10 to the second power times 10 to the third power. And sure enough, this is 10 to the fifth power. So exponents add together. When you take the log of 100, that's 2. When you take the log of 1,000, that's 3. And sure enough, 2 plus 3 equals 5, which is the log of 100,000. Therefore, the log of 437,000, you can think of that as being the log of 437 times 1,000 in parentheses. Why, that would be the log of 437 plus the log of 1,000, which now you can do in your head, because the log of 437 we wrote down as 2.64048, and the log of 1,000 is 3. So the answer is 5.64048 is the log of 437,000. Here's my proof. I turn on my calculator. and I ask it, what the heck is the log of 437,000? It says, I was always right. 5.640481437, which is the log of 437 plus 3. Nice. Now, let's struggle with 2 to the 0 power. What is 2 to the 0 power? Indeed, 2 to the 0 power is 1. Any number other than 0 to the 0 power is 1. 2 to the first power. 2 to the first power is 2. 2 to the second power. 2 to the second power is indeed 4. 2 to the third power. Indeed, 2 to the third power is 8. 2 to the fourth power. So there's a pattern here. Whatever number we start off with, typically 1, we now double it, double it, double it, double it to 1, 2, 4, 8, 16, and so forth. What if I wanted to find that value of x such that 2 raised to the x power is equal to 13.7? Suppose I want that value of x such that 2 to that power of x, that value of x, ends up being 13.7. Well, I can tell you by looking at what I've written so far that x must be between 3 and 4. And beyond that, I can't tell you unless I have a calculator with a log function. So what I can choose to do, because we love math, is take the log of both sides. So the log of 2 to the x power would be equal to the log of 13.7. So the log is an operator like adding or multiplying or dividing. I would say multiplying or dividing are the better choices, not adding. So if I said, 2 times 5 equals 10, and then I said, okay, I'm going to multiply both sides by 3, this is still going to be true. If I say divide both sides by 10, this is still going to be true. Well, this was true. And by choosing to, in fact, if I choose to take the log of 2 times 5 and say that's equal to the log of 10, that's still a true statement as well. So taking the log of both sides doesn't make it untrue. It's still a true statement. Maybe you realize this earlier property about logarithms is that the x can be pulled out now. And this becomes x times the log of 2 is equal to the log of 13.7 in this example. Now I can solve for x. Oh man, this is easy. X would be equal to the log of 13.7, which I can ask my calculator, what the heck is that, divided by the log of 2. And I can also ask my calculator, what the heck is that? So here we go. And by the way, no, you can't divide 13.7 by 2 first. That would not be correct. What you can do is ask it, what is the log of 13.7 divided by the log of 2? Enter. And it says, oh, clearly, you foolish human, the answer is 3.7761039888. Yeah, sure, let me write that one down. 3.77610610. Okay, close enough. Here's my claim. I can prove this to you. by asking it, what do I get when I raise 2 to that power of 3.77610? On your calculator, if it's a TI brand, you could use the caret symbol to raise it to that power. On a Casio, it might be the EXP button. I'm not sure. And if you have your phone app, that is the X to the Y button. So either way, you have the technology. So 2 raised to the 3.77610th power is, boop, well, I didn't type in all those digits. So this thing is 13.69996,213. If I put in more of these digits, it would land closer to exactly 13.7. But I'm going to, make you believe me. This thing is 13.7. Great. Back to half-lives. The final mass is equal to the initial mass times 1/2 raised to the number of half-lives. To solve for the number of half-lives, if we know the initial and final mass, I would first divide both sides by the initial mass. So I have final mass divided by initial mass is equal to 0.5, because that's 1/2, 0.5, raised to the nth power, where n is the number of half-lives. Great. So how do I solve for n in this horrible looking math problem? Well, the answer is we're going to take the log of both sides. If I take the log of the left side, that means the log of, open parentheses, the final mass divided by the initial mass, close parentheses, is equal to the log of, open parentheses, 0.5, which is 1/2, raised to the nth power, close parentheses. I'm hoping you know what to do next. We're going to pull this n out and stick it in front of the log. Now we have log of the ratio of final mass over initial mass, some number, is equal to n times the log of 1/2. Solve for n. N is the log of this ratio, final mass divided by initial mass, divided by the log of 0.5. Ta-da! Let's practice this equation. So I'm going to write it one more time, somewhere where you can see it. N is the log of the ratio of final mass over initial mass divided by the log of 0.5. And not that it matters to you students, but last period we established this also works if you do it using natural logs. You get the same result. Just pick one and stick with it. Okay, we need an example. What is the initial mass that we have to start off with? All right, so we have a random value for an initial mass of 98, we'll say 0.0 grams of some substance that undergoes carbon-14 disintegration over time. And for this particular example, some unknown number of years go by, and after all those years, we end up with a final mass of, all right, our final value will be a measly stinking 2 grams. All right, we just had our 3-minute break, slight disruption. And now we're going to solve for n, right? So what we have is 2 grams is equal to 98 grams times 1/2 raised to the mystery power n, the number of half-lives that have gone by. Thanks to modern math, we could say that n is the log of 2 divided by 98, and yes, make sure you do it in that order, divided by the log of 1/2. Using my calculator, the log of 2 divided by 98 divided by the log of 1/2, I get 5.614709844 as the value of n. N equals what I said, 5.6147. Close enough. That is the number of half-lives. As you might remember from way back on page 1, maybe, the number of half-lives is equal to the age divided by the half-life. I know I wrote that someplace. Oh, well. So this is equal to the age of the sample divided by the half-life of that sample. In other words, to find the age, we multiply this number by the half-life. And the half-life is 5,730 years. So if I power up my calculator and I go times, it implies that I mean times my previous answer, 5,730, enter. There's the answer. The age of the sample in this example is 32,200 years. Okay, we'll do just a couple other examples to finish out this review. If I have an initial mass of 47.2 grams, and time goes by, and this will be carbon 14 again, and time goes by. So let's say 2,000 years go by. How much sample is left afterwards? Well, the formula is the final mass is equal to the initial mass times 1/2 raised to the number of half-lives. So in this case, we would say 47.2 grams times 0.5 raised to the power of, I'm putting parentheses all over the place for no reason, 2,000 divided by 5,730. The years will cancel. And 47.2 times 1/2 raised to the open parentheses, 2,000 divided by 5,730, close parentheses, exit, enter, is 37.1 grams. 37.1 grams is the final mass in this example. I suppose finally, what if I only knew the age and the initial, the final mass? Okay, suppose I have a final mass of 12.2 grams. Probably should not do micrograms, should just do grams. And I happen to know that the age of this sample is 30,000 years. If this is what I have left after 30,000 years go by, How much did I start with? Well, the formula is final mass equals initial mass times 1/2 raised to the number of half-lives. To solve for the initial mass, I divide both sides by this term. So final mass divided by 1/2 raised to the number of half-lives will give me the answer, my starting mass, my initial mass. So on my calculator, I would go 12.2 divided by 0.5 raised to the open parentheses 30,000 divided by 5,730 close parentheses, escape from this, enter, and it says quit. Oh man, I thought I was doing so well. 12.2 divided by 0.5 raised to the open parentheses 30,000 divided by 5,730 close parentheses, escape from dissenter. And there's the answer. My initial mass was 460 grams. 30,000 years in the past, I started off with 460 grams, and now 30,000 years later, I'm down to a measly stinking 12.2 grams of carbon-14 stuff. This ends this little tutorial.